We expected a few more people in costume, but I think they've gone to the other venue, wherever the other venue is. I'd like to first of all, before I introduce bernardCACHE, I would like to thank Springcrest for supporting this evening and for giving us the opportunity to sponsor, not only to sponsor forum, but also help with bringing Professor Cache from Paris to give us this lecture this evening. So thank you very much, Springcrest. We will try and have a little conversation afterwards. There was good feedback from last week. It's actually only a week ago. Wow. Last week with Edward Francois. So I will introduce those that will come up to the podium afterwards. But first of all, I would just like to introduce bernardCACHE, and I will do this by, I'm calling this 10 things I picked up about bernardCACHE over oysters, scallops, and beef tartare in whalebone last night. I won't mention the amount of Miller's Stout we had, which was excellent with the oysters. Number one, he wrote the first book in the series called Writing Architecture out of MIT Press, called Earth Moves. The book is dedicated to Gilles Deleuze. 2, he is a scholar who knows mathematics and antiquity and computing, but he believes they all shape our contemporary life. He has a factory in Paris, number 3, not an office, called Objectil. He may have to sell that factory due to the disaster happening in Europe right now. He speaks 5 working European languages: French, English, Italian, German, and Spanish. He speaks 1 African language, Susu. He can glide across Euclid, across geometry from Greece to Egypt, but is irretrievably rational in his being. He believes the antique culture is so much more important than it is allowed to be today. His last book was called Projectile, out of the AA in London. He wrote about Obama and Bush also. His next book is on Dürer. Number 8. In Finland, he gave a lecture called The Parametric Vitruvius. No, he didn't. I invented the title, but he did speak on Vitruvius. He has 2 daughters who, addicted to Facebook and smartphones, do not understand how their father, without a smartphone, is so much more digital than they are. He breathes computing, number 10. He breathes computing to shape our world, not to be a slave to it. Welcome to bernardCACHE.
Thank you very much, Roger, for this very kind introduction. What I would like to do tonight is to show you that parametric design and mechanics are not new in architecture. They are there from the very beginning of the written sources of our discipline. And to understand that, we have to come back to classics such as Euclid, Plato, and Vitruvius. My guess is that a renewed reading of those classics has the potential to bring contemporary architecture back into a historical tradition. And in order to demonstrate that, I will mainly rely on a middleman, Albrecht Dürer, the greatest artist of the German Renaissance, who lived at the turn of the 16th century in a period that is roughly somewhere between our times and antiquity. But instead of showing you his wonderful paintings, I will mainly focus on his treatise of geometry the Unterweisung der Messung, or the instruction for measurements. This is a treatise of geometry that is written by a non-mathematician for non-mathematicians, just like you. Actually, Dürer was a painter, educated as a goldsmith. He wrote for all kinds of craftsmen, among which carpenters, stonecutters, and architects. And this explains that this treatise is organized by figure and not by propositions, as Euclid's treatise. Dürer explains procedures rather than making demonstration, although we will see there is one very important exception. Actually, very often, rather than geometrical figures, what Dürer shows are mechanical instruments intended to draw curves that sometimes are not even represented. These practical terms explain that in order to read this classical text, we need a CAD/CAM software which enables us to establish parametric relations between elements in the figure, or model the mechanical instruments and simulate their movement in order to generate their trajectory. That you have to bring mechanics into the field of fine arts, this should not surprise us if we come back to the main written sources of our discipline, the De Architectura of Vitruvius. Indeed, the topic of the De Architectura is not at all restricted to Greek temples, neither to the three classical orders, Doric, Ionic, and Corinthian. I don't know if you remember, there are two definitions of architecture in this treatise, and the second one is the following. Architecture consists in three parts: the construction of buildings, edificatio, the construction of solar clocks, mnemonica, and the constructions of machines, machinatio. And this definition is very important because it shapes the table of contents of the De Architectura. If you put aside book 1 and 2 that are kind of introduction common to all of those three parts, you have then book 3 to book 7 which are dedicated to edificatio. Then you have book 9 dedicated to mnemonica, and then you have book 10 dedicated to machinatio. I would not make a kind of in-depth analysis of this classic text, but of course there seems to be a disproportion between edificatio and machinatio, but just let me explain you that the book 10 on machine has in itself as many pages as the book 3 and 4 on temples. And in addition, the first building mentioned in the De Architectura incarnates this definition of architecture. This building is the Tower of the Winds, built by Andronikos the Kyros in Athens, approximately in -100. So this is the building in the state you can see it nowadays, and you see it from the rear, where there was here a kind of little cylindrical tower, which you will see was actually a water tank in order to power a machine. So obviously this object is a building, edificatio, and I have to convince you that it was also is part of mnemonica, and that it is also a machine. So let me show you here the drawing of the famous English travelers James Stewart and Nicholas Revett. And they indicated very clearly the small lines that were actually the hour lines of the sundials on those buildings. So those lines, what is important, it is that those lines comes actually, are drawn in each of the 8 walls of this octagonal building and create a different network on each of those walls. But those different networks come actually from one single diagram, which is a geometrical diagram that you find the explanation into Vitruvius' book on mnemonica. So it is a parametric figure, and then we come to the software. So here is the analemma as it is described by Vitruvius. And this is a parametric drawing that depends on 3 main parameters. So the first one is the month of the year, or the period of the year. The other one is the latitude. And most important, there is also the orientation of the walls. So if I'm changing here this orientation, you can see how this diagram deforms. Okay, so actually this sundial is of course on a planar wall. And actually Vitruvius does not describe everything into this diagram, and especially he does not provide a procedure to project the curve on a plane. And one possible reason for that is that actually most of the antique sundial were not planar, but were actually drawn on curved surfaces. So here I have a catalog of all the antique sundials known today, and you see that on 254, only 40 were planars. So here you can see examples of sundials on curved surfaces, and actually the expert at multiple curved sundials was Andronikos the Kyros, the architect of the Tower of the Winds, which is precisely the building I showed you. So I just hope you start to be convinced that the Tower of the Wind is really part of mnemonica. Now let's switch to Machinazzo. So this is a plan of the building with the traces of the mechanism that remain on the ground floor. There was actually, in the internal of the building, a huge mechanical device where water was spilling from the cylindrical tank at the rear of the tower that I showed you before, down into a lava in a tank, and there a float was lifting a cable winded around an axis which had the big bones rotate. So this is more or less the section. So the question is, what was this disk about? And actually, it was a stereographic projection of the celestial sphere. So if, in case you do not remember what a stereographic projection is, let's look at its principle. You take a sphere, and you take any point on this sphere, then you trace a diameter passing via this point, so here it is a point at the summit of the sphere, and you draw a plane orthogonal to this diagram, to this diameter. And what happens is that circles on this sphere project onto that plane not into ellipses, but into circles. And even more important, the angle that makes the tangent of the circles on the sphere is equal to the angle made on their projection on the plane. And of course, this is also a kind of geometric parametric design. So you see here this dimension of 161 equal to the other one here. Okay? And in case you would think this is just all the geometry, I would remind you of Henri Poincaré, the French geometer, who at the beginning of the 20th century used precisely stereographic projection in order to provide a geometrical model for non-Euclidean geometry, what is so sadly called non-Euclidean, whereas it is just an alternative to Euclidean geometry that actually validates the necessity to have a fifth postulate rather than invalidate his geometry. The German mathematician Felix Stein would say the so-genannte nicht-euklidische Geometrie in order to say how badly called was this geometry, the new modern geometry. So let's come back to this big bounce disk into the Tower of the Wind, and let's see what was the main problem there. Actually, people tend to think of, antiquity as people who had a kind of simple and much more simple analysis of time and space than we have. Whereas actually it's just the contrary, because already the unit of time was variable. Because all along the year, the duration of the daytime was divided into 12 hours, which means that the hours in the winters were shorter than the hours into the summer. So the problem becomes, how can you measure a variable phenomena with an instrument, this huge bounce disk, that rotates at a constant speed? The solution is that you provide a network of conversion curves that are placed in front of the disk in order to divide. So here you see the blue line, that's the horizon, and the red curves divide the circles above the horizon into 12 little arcs that have the same length. And it does the same for the night hours. So let's see that here on the software. Here you see the disk rotating, and this is the position of the sun, which changes according to the period of the year, and you see it rotating and indicating the hours that are marked by the red lines. So I hope to have convinced you that this is really a sophisticated machine. And so the first Vitruvian building is not at all a classical temple. This tower incarnates the three parts of architecture, since it is a building, edificatio. It bears 8 sundials, one on each of the 8 walls of the octagonal tower. But above all, it is a machine. And it is not a machine for living, une machine à habiter, as would say Le Corbusier much later. But it is a machine that produces information, what we would call today a computer, from the Latin verb computare, or to calculate. And precisely, Dürer inscribes himself within this antique tradition of variation, both parametric and mechanical. And this is what I want to show you this evening, because the main point into Dürer's geometry are actually instruments, either drawing instrument or calculating instruments. And actually, because Dürer is the first author to write a treatise in German, he will have to invent names in his German language, and for that he will use the name of animals. So this evening we'll eat 3 animals, first the snail, then the spider, and then the snake. So let's start with the snail. It its origin comes actually from Vitruvius. It comes from the description of the unical volute that you find in Book 3. Unfortunately, Vitruvius' description was rather hard to understand. His text is not very clear, but above all, he was alluding to a figure at the end of his treatise, and as you know, all of the figures of Vitruvius have disappeared. As a result, Dürer's volute is erroneous. Although since 1518, Antonio da Sangallo had already provided a correct interpretation of Vitruvius' description. And I think it is good to come back to the original method indicated by Vitruvius, because you will understand that this is already fully mathematical. Let me explain you. You take the circle of the oculus at the center of the volute and you place 4 nails. And then around those 4 nails you wind up a thread, and of course each time this string is intercepted by one of the nails, the length of this thread is reduced by the value of the interval between the 4 nails. So this actually creates a series of ranges that diminishes, and do that according to an arithmetic series by which you take off 1 unit each time you do a quarter of circle. So now it is only the 6th figure of Vitruvius' treatise, so he goes very, very quickly to already a complex curve, you know. And the 7th one, Dürer's comment is the following: now I will draw another spiral by a different method, which can put to many uses and is very useful. I think we can assume what is important is that now I will draw another spiral by a different method, because it is a general principle in Dürer's geometry that there is nothing asserted into a figure that cannot be submitted to variation into a following figure. So we have to understand how from Vitruvius' volute we arrive at Archimedes' spiral. So let me remind you of this spiral. There it is. And so let's do the simulation. So at the same time a radius rotates around the center, a point moves on the radius, and this traces the spiral. So think of the 4 nails, and now you place it closer and closer until the point they reduce into a single point, and you consider that point having no thickness. So then you can wind up your thread all along, and the length of the string will never reduce, because this point has no thickness. So this is a problem that is well known from antiquity. This is a non-mechanical curve. It cannot be achieved with a mechanical device. So Dürer invents what I would call a digital device, by which he divides here the radius into 24 parts, equal segments, and then he divides this circle into 12 arcs, and he associates point 1 of the radius with angle 1 on the circles, and this enables him to construct this curve. This is what we do with the computer nowadays, which is of course a digital instrument. But now, look, next figure. Now I shall alter the previously made spiral once more by means of a demarcated ruler. And so Dürer provides this drawing here, which I call a diagram, and to me, the definition of a diagram is that it is a mechanical drawing that organizes a variation. So it is not the figure in itself, it is not the final output of the parametric model, but it is the tool that organizes, that regulates the variation. So look well at this diagram, because we have to understand where does it comes from. And actually, in order to understand that, we have to go a bit further into Dürer's book in the parts that deals with solids. And actually, those solids are architectural columns. And then immediately after this section starts a section dedicated to the drawing of the letters of the alphabet. And the first picture into this section is this one, where you have a tower with varying letters. So those are the first words of the Lutheran Bible. And what you recognize here is the diagram that I showed you before. So for your memory, there it is. So in this diagram, Dürer divides the circle into equal arcs. Those are the apparent angles of the letters, and then he projects those equal arcs onto a vertical plane and giving varying height to the letters. What is very interesting here, it is that actually this is more close to the optics of antiquity, where the image is an apparent angle, rather than to perspective in Renaissance. But Dürer was also a theoretician of perspective. You, of course, all know this wonderful drawing. Perhaps you know it more for the object of the perception rather than for the eye of the observer. But the eye of the observer is precisely the important point, because actually this is the first image of a series of 4. So this is the second one, where you also have the eye of the observer. Then the third one, where you also have an observer with an eye. And then the fourth one, when you have no more observer, no more eye. This is a totally mechanical method. This is, I would say, the first computer image. So Dürer was really talented into perspective. He's the first one writing in German about this topic. But just as Leonardo da Vinci, who was also a very good connoisseur of perspective, Dürer was still attached to the perspective of antiquity. So I remember the problem of Leonardo da Vinci, who had to represent a series of spheres, and who will never admit that in the end you have to represent it as an ellipsis. You, of course, all know the counter-project of Juan Carmel de Lobkowitz for the piazza that Bernini's drawn in front of St. Peter in Roma. And of course, the section of all of the columns drawn by Bernini were circular. And Juan Carmel would criticize that fact, saying that he wanted an equal apparent angle at a circular distance from the center, and this would create elliptic and even more varying elliptic column all around the piazza. So here you see it even more developed into this drawing. So all of this brings back to optical corrections, and the principle is to deform the deformation in order to restitute original proportions. So it is a kind of second level method, a deformation of deformation. For instance, on Dürer's towers, the letter have a varying height in order that deformed by the apparent angle, they maintain a kind of constant proportion between themselves and appear equal. So now let's come back to this drawing. Even within this diagram itself, you see that Dürer starts to project the arcs onto a vertical line, but then he says immediately, why not have an oblique line and project those arcs onto this varying oblique line? So this is really a parametric model. And the problem is now how you use that into 3D space, since the model that presents us Dürer, and this is only the 8th figure of his Treatise of Geometry, is this following one, where Dürer clearly anticipates on Monge's descriptive geometric method. So you see here in plane the 12 angle around the circle, and then you see here the points in elevation. So we have to see that into 3D and simulate that onto a modern computer. So here is the diagram, and of course in this everything is parametric. And now we will play the simulation. Okay, so the radius moves at a constant speed along the arcs and project onto a variable speed onto the oblique line, and this makes that the red line of Dürer is different than the green one of Archimedes. But of course, it is a family of lines. There has as many red lines as angles in which you incline the line on the diagram. Okay, so where does that lead us to? Directly to architectural application. So if you go into book 3 of this book of geometry, as I told you before, what you mainly find are architectural elements, and especially columns. And you can see here, you recognize this diagram that is used in order to make a spiraling, well, a varying spiraling fluting on this column. And here you see that even the main shaft of the column is transformed into a varying spiraling one, much more complex than the column of Bernini's Baldacchino in St. Peter. So let's check that this provides us with a valid method for nowadays. So let me open this document, and I made a parametric model of those columns, and let's check how it works in modern time. So here I have included an additional column. I will give it a specific height, and now the only thing I have to do is to make a positioning of this frame onto this frame, and there I get a new column. So all of this is of course fully parametric. I can move the point, I can edit the column and change their height and also their shape. This is a direct translation of Dürer's method. So, what is very ironic into this is that it is only after having shown the varying spiral that Dürer mentioned in passing the regular staircase with a regular helix, just to show you that he's not interested by regular things. He's interested into having things vary in a way that is parametric. So we have now eaten the snail, we still have the spider. And he starts saying there is another type of line which I call the spinning linear, so the spider line. So this is the drawing that Dürer provides us, and of course, again, we have to make the simulation if we want to understand this. So here is the instrument, and now you understand that we switch from a totally digital instrument into a real mechanical one, and we will have it rotate in order to understand what it is doing. Again, this is fully parametrical, and I can change the parameters. And you can see that actually there is an infinite variety of those curves. So why was this instrument called Spider by Dürer? So you remember this drawing, he calls that probably a spider. One of the reasons is that the position, the instantaneous position of each of the mechanical arms that you've seen on my instruments resembles many legs like in a spider. But I think they are also the representation of the various positions of the human body in motions. Okay, if I would move and keep track of all my position while I am moving, you would find this type of drawing, which were actually drawn by a disciple of Leonardo da Vinci, whose name was Carlo Urbino di Crema. And you can see here the concrete drawing, but you can see here an abstract drawing where you can clearly see that he's using this method. And you must remember that in Vitruvius' treatise, Vitruvius mentions the name of a solar clock as an arachneia, which is a Greek name for spider, that he attributes to Apollonius. And Apollonius was a very important Greek mathematician, living in writing in minus 220, who also worked on astronomical models in order to describe the apparent retrogradations of the planets with a combination of uniform circular movements. So the first big circle is called the deferent circle, and the other one, the little one on top of that, is called the epicycle circle. And as you can see, here you see the various hypotheses that were useful in astronomy. Here, the retrogradation loop. Here, the circle used in order to explain the varying length of the season provided by the sun. And look, you can also generate an ellipse if you want. And then, of course, you can generate many, many other curves. So in the Renaissance, the same principles were applied to the movement of two types of bodies: the human body and the celestial bodies that were the planets. So does this same principle of motion for celestial and human body necessarily leads to conceptions of harmony between microcosm and macrocosm? I'm very doubtful about that. Let's come back to one of the pictures of Carlo Urbino di Crema in order to appreciate how contemporary they could be. They could be from a modern palette. Okay? But obviously, behind Carlo Urbino di Crema's drawing stands the famous drawing of Leonardo da Vinci that I show you in small, but that I will make a zoom on top of it. And look at this drawing, which is very often described as the example of perfection and harmony in Renaissance. Actually, nothing coincides into this drawing. Just look here, of course, the lower end of the square have no relation to the circle, but neither this one too, and it is very uncomfortable to analyze that. Now, look at this drawing. Actually, this drawing is a montage made by Leonardo da Vinci on the basis of two consecutive paragraphs of Vitruvius in the De Architectura. Because Vitruvius speaks first of the body lying on the ground, supinus in Latin, that is inscribed within a circle, the center of which is the umbilicus. Well, the umbilicus in English, I think you understand. And then afterwards, Vitruvius switches to the body standing up. The Latin word is erectus, inscribed in a square, the center of which Vitruvius doesn't mention because they were very polite at the time, but was sex, or as Weber would say, what makes the difference between man and woman. So Vitruvius takes two passages of, Leonardo da Vinci takes two passages that are one after the other, because Vitruvius never says you could put the square on the circle, they would inscribe one into the other, and you would find one unique center, both for the body lying and the body standing. Vitruvius never said that. So it is a montage made by Leonardo da Vinci in order to make us understand that things do not coincide. I think that this is not even new for Leonardo da Vinci. If you come back, for instance, if you read Weber's De Lingua Latina, that is a text mentioned by Vitruvius, so it's not external to this written tradition. Weber says that in the world there is an apparent center, which is a Greek religious center of the city of Delphi. Just as in the human body you have an apparent center, which is the umbilicus, but actually the effective center of the earth is down into the underground at the center of the earth, whereas the effective center of the human body is what makes the difference between men and women. If you switch to a much later text from Theon of Smyrna in plus 120, reading mathematical knowledge useful for reading Plato, you would see that Theon of Smyrna speaks of two centers of the world, one called geometric center, which is the earth, and one hot dynamic center, which is the sun. So the discussion about the center of the plurality of the center of the world has never stopped from antiquity, because of course there was the hypothesis of Aristarchus of Samos about the sun being the center of the world, but there was also the Pythagorean who had the idea that the sun was the center of the world. So let's come back to Dürer now, whose main mathematical mentor, Johannes Werner, was actually in relation with Copernicus. And then all these topics were actively discussed in Nuremberg while Dürer was writing his treatise. And if Dürer writes a treatise on geometry, being a painter, it is because he has a more general project, which was to write a treatise on painting. But he has too big ambitions, and he does not succeed into making this big treatise he would dreamed of, to rewrite a De Pictura, a kind of German De Pictura, which would echo the Italian De Pictura from Alberti. So Dürer decided to split his big project, and actually he writes 3 different treatises. First, the geometrical treatise, the Unterweisung, and then another on human proportions, and then another one on fortifications. The fortifications, and then on human proportions. If you look at the one on human proportions, you would see that there, Dürer rejects totally the idea of one single perfect system of proportions. He starts distinguishing men and women, but also adults and children, and then different temperaments, resulting in a system of 38 types that are just the beginning of a system of variation, because on top of that, he creates topological deformation that you can, of course, do with contemporary software. And, of course, on top of that, there are the problem of movements, since the proportion of the human body varies with its movements. But in order to do that, we have to switch from the spider to the snake and go into another instrument. And this is these instruments. Actually, this is the only thing that Dürer shows us about the spider, the snake line. Where do you see it? It is not even drawn, whereas he showed us that he was able to use Morge's method in order to draw very complex spirals. So we have to build this line ourselves, and this is what I will do with software, and I just hope to convince you that software can also be useful in order to make history. So, this one here, so this is the instruments that is drawn by Dürer, and now we will generate the curve. So here is the movement, and I will generate also the trajectory. So I want the trajectory of this arm here, on this point here, and I want it to be this spline, and there it is. Okay, and for instance, thanks to parametric software, I can, for instance, edit this arm and substitute another one and validate. Oh, sorry, I must do something else before. But so you can substitute all of these elements, and this regenerates the trajectory. So what I would like to convince you, it is that this is not one single snake curve. It is a whole variety of them. And precisely, this is what Dürer insists upon. So these are his words. In the following, I shall show how to construct an instrument that can be used to draw a variety of lines, including a serpentine line. The rods shall be arranged in a manner that can be advanced by degrees and can be shortened or extended. The instrument should also be made with few or many dials of rods, so he made the number of rods vary. And the rods can be pulled apart or pushed together, also by degree, so that they become shorter or longer. So what is then this serpent that Dürer refrains from drawing while he describes a machine that generates a whole variety of those snakes? I think a plausible hypothesis is that this serpentine line is the serpent of the Laocoon that was precisely uncovered in 1506, precisely at the time when Dürer makes his second trip to Italy. But the most important, if you come back to Dürer's drawing, so there are his images, actually the most important is not, of course, the line that you do not see. It is not the instrument, but it is this diagram here, into which Dürer is organizing the variation of the different arms of this instrument. And actually, if you go a bit further into the book one dedicated to the lines in the Unterweis und der Messung, you would find only this type of variation diagrams that are here. So there are actually 12 of them. And actually there was an additional one that was added by Camerarius, the translator in Latin of this treatise of geometry. And Camerarius, I can think he added the sentence, this diagram can be used for many purposes. And indeed, we find this diagram both into the treatise on human proportion and into the one on fortification. And here, well, Dürer calls it the Vergleicher, which is a kind of German translation of the comparator, if you would say it, translate it literally from in English. So here is this diagram in the Treatise of Fortification, and let me show it to you in 3D. So, into the main topic, into his Treatise of Fortification, is how to build the circular wall in front of a bastion. And so, the first, actually there are two diagrams into this description. The first one is the one that you find here, and that corresponds to this. So, all of the line converge on the front towards this line, this point here, and all of the line in the rear converge towards this point here. And Dürer explicitly says that those points have an arbitrary altitude. So it is already a kind of parametric model. So now, the problem of Dürer is to organize the circular walls. So how does he design it? So I place here into the same drawing the drawing of the bastion itself and the diagram he is using, that is this one here. So you just have a series of lines that converge onto regular interval, onto a vertical line. And now, the first interval intersected by this oblique line corresponds to the thickness of the external circular wall. So now, this distance here corresponds to the total length of the oblique line. So that means that if we change this dimension and make it, for instance, 77, and now change the thickness of the wall to 22, you see that this line is moving onto this diagram. So let's see the final result. This is the drawing of Dürer, the section throughout the circular walls. And you see that it is already a kind of complex architecture. But what is the main point? It is that this diagram that seems to you as something probably very simple is actually not drawable just with the ruler and the compass, since when I'm moving this oblique line here, be very careful because its lower end here does not follow a straight line, but actually a complex curve which is of the 4th degree. It is not very visible, but this is what is the accurate line. So this is the reason why Dürer has to use other instruments than just a ruler and a compass in order to establish his diagram. And here you see it clearly drawn as an instrument with a real thickness for the oblique line. Now, this is also used into the Treatise of Proportion in order to regulate the dimension of the trunk as compared to the thigh, and then the thigh as compared to the shin. And this is organized as a continuous proportion where Dürer says the trunk is to the thigh what the thigh is to the shin. So it might be that you do not remember what a continuous proportion is in Greek mathematics, or also in modern mathematics. So a continuous proportion is a series of fractions that are all equals and that have at their denominator the numerator of the next fraction. And when this is restricted to 3 fractions, this is called a double proportional means. Why do I go into those details? It is because already in minus 430, Hippocrates of Chios will demonstrate that if you establish that establishing a double proportional mean is equivalent to find out the side of the cube of a given volume, or said in modern terms, to calculate a cubical root. And indeed, provided we have this continuous proportion here, in the particular case where A is taken as a unit, which means when A equals 1, there you would find that x is equal to the cubical root of B. And of course, when B is equal to 2, then x is equal to the cubical root of 2. And this is the problem of the duplication of the cube. This problem is important because it is one of the 3 main problems of what is called superior geometry in Greek mathematics. And what is the border between superior and elemental geometry? The border is that superior geometry are the problems that require to draw curves that cannot be traced with a ruler and a compass. But be very, very careful, because this is not only a theoretical problem, it is also a very practical problem, for instance, for volume calculations, but also for the calibrations formula of the war machine. Since the war machine of the Greek and then the Romans were of that type with 2 springs through which you would pass a wooden arm, and then if you would pull those arms, you would pull the strings into torsion, and releasing the arms, you would project the projectile, which can be either an arrow or a stone. And according to the nature of those projectiles, the formula in order to dimension the diameter of those springs was different. This is, of course, described, we know about it, via Vitruvius. And Vitruvius is not inventing, because we have treatises of mechanics that dates back for much before Vitruvius that have the same type of formula. So for an arrow, the diameter would be 1/9 of the length of the arrow, the diameter of the spring. And for a ballista, which is the war machine that projects stones, the diameter would be 1.1 multiplied by the cubical root of the weight of the stone you want to throw. Actually, Vitruvius does not provide the second formula, but he gives us a table of value that correspond to this formula. And in book 9, before book 10 dedicated to the machines, Vitruvius mentions two solutions of the cube duplications. Let me show them to you. The first one is the one from Archytas. So suppose this chord is the length unit and the diameter is the length you want the cubical root of. So what do? You draw a torus, and then on top of this torus you build a cone. And of course these two solids intersect into a curve that is not planar, as you can see here. And now, in addition to that, you draw a cylinder on top of the circle, and this cylinder intersects the curve into a point that you can see here in black on this drawing. And then you have the definition of a plane into which you can draw this geometrical construction. And of course, all of this is parametric. I could change the diameter of the circle and rebuild the whole of this already complex geometry. So now this was drawn. Archytas was a great friend of Plato. So Plato would visit him each time he would go to Sicily. He went there three times. Because Archytas was living in what is now Taranto in Italy. And of course, it is an extraordinary method, but it is, and especially if you think that he had no computer, no 3D software, and that those are probably the type of images he would draw on the sand, on the beach, in Italy. This is the image drawn by Sir Thomas Heath in his own History of Greek Mathematics. So as you can see, you should have a very clear-cut 3D intuition of space in order to draw that at that time. But it is unfortunately totally inefficient. Suppose you are on the battlefield and you have to build your war machines. Would you sculpt a torus, provided you are able to sculpt it in an accurate way, then sculpt a cone, and then a cylinder, and then make the intersection reproduced in Modena, in Italy, at the Unimo Museum. But we can make it work here. So you have three plates, one on top of the other, and then you have a string here, and the game is to move the plate in order that the intersection point here, B and G, be aligned on the string. So when one has some kind of training, you can succeed in approaching the solution. What is important is to understand that this is an iterative process, because once you have 3 points aligned, bringing the fourth one also modify the angle of the line. So it is an iterative process that never ends, but actually converge rather rapidly. So now, how do we know about all of this? Well, we have a lot of commentary. This is, for instance, Descartes' commentary into his geometry. But there is a catalogue of all the methods of cube duplication that was made by Eutychius at the end of antiquity. And actually, Eutychius was a colleague of the architects who built Hagia Sophia in Istanbul. So Dürer mentions three of those solutions to the cube duplication. One is from Spurs, the other one is from Heron, and the other one is attributed by Dürer to Plato, just as Eutychius also attributes it to Plato. So let's look at this solution. So suppose now you have here this very simple type of drawing. So of course you have here three similar triangles, and this enables you to quickly demonstrate that BE on DB is equal to DB on BC and BC on BG, and G being the minuscule one, the small one. So you immediately get here a double proportional mean. So why all this fuss about the cube duplication if you can draw this very easily? The problem is to make coincide this G with the other one. And this you cannot ensure with a ruler and a compass. In order to do that, you have to use an instrument, and this instrument is here drawn by Dürer, and this is the one that is erroneously attributed to Plato. So let me quit all of this and show you the instrument. So there it is. You have one square that can move like this, and here you have a point that describes a trajectory, and the solution is when the trajectory intersects what would be for us the equivalent of the y-axis. And of course all of this is fully parametrical and could be adapted to the square root of 2, square root of 3, and even additional type of square roots. So, as I told you, this attribution is false. To be sure, this instrument was not designed by Plato. Actually, it was most probably designed by Eudoxus. And Eudoxus is a mathematician who happened to live at the time of Plato and who even visited Plato at the academy. And one of Eudoxus' great achievements is that he provided the first mechanical model in order to describe the retrogradation of the planets, a topic we already talked about. So let me show you how it works, because you would not think that this was invented in minus 365. I think it's quite amazing. So now, what is important is not the fact that Plato did not actually design the instrument that enables to calculate the cube duplication. What is important, it is that this false attribution proves that there has been reading of Plato that were not idealist in antiquity. I think that we have a totally single-minded reading of Plato when we trust Plutarchus and his description of Archimedes as being disturbed by having to build war machine to defend his city of Syracuse. I think that in antiquity, all of those people were much more interested by mechanics and actually concrete applications of geometry than is most often recorded. And I would conclude saying that the classical is not necessarily classic. It means invariable, symmetric, ideal, abstract, or harmonic. More precisely, there is a plurality of traditions in antiquity, and the tradition Vitruvius and Dürer belongs to put the emphasis on parametric and mechanical variations. we've seen that the Tower of the Wind is already an information machine. The ballista is also a war machine, the main parameter of which depends upon a complex mathematical formula with a cubical root that is in its turn calculated by a mechanical instrument, the type of which, for instance, we've seen from Eratosthenes, or the one from Eudoxus attributed to Plato. The temples themselves were the result of a complex parametric conception due to optical corrections, at least in the De Architectura. Thus, Vitruvius provides us with no absolute values, but only with proportional ratios that are actually parametric coefficients. Hence, parametric design is not new, and mechanics were an essential part of architecture since antiquity. And it is precisely on those grounds, parametric design and numerical command machines, that you can think of inscribing contemporary architecture within this other classical tradition. Thank you.
I have the feeling that we've just had the prologue, and now we could have the contemporary, and we'd see how the classical would go into the contemporary, but we won't have time for that tonight. Might I suggest we have a small conversation if we can? We're 7:25, so we'll try and have 20 minutes. Could I ask our director, Marco Frascari, to come up and perhaps respond to Bernard? Can I ask Bernard to go on the stage? Janek, would you like to come up? And we have Janek Alford, who was a master student here and has started his own company here called Prototype D, and Ryan Steck, who is a master student in architecture now, but he's in charge of the Electronics Festival in Ottawa and works with Art Engine. I would like to ask them to address a few of these issues in a short 15 to 20 minute discussion, if we can. Marco Frascari, as you know, is the director of our school, the Adriani School of Architecture and Urbanism. Also, someone who speaks about Vitruvius in many ways, perhaps in many different ways, but I would like to ask Marco perhaps to respond to Bernard's point, especially perhaps the points that are left on the screen at the end, where the classical tradition is redefined. Marco, the floor is yours.
Okay, I'm not going to follow your suggestion. What I'm going to do is to point out immediately that what I think it came out tonight is the great misunderstanding about what is parametric design. And I think the work that was presented is really delineating what parametric design is. The problem I have is the parametric design of Dürer and Vitruvius and company was based on tacit knowledge. In the sense, there was no explanation on how the tool worked, mathematically speaking. There was only the tool. They had it in their hand, they used it, and they built it. Then, of course, the mathematician came aboard, and they invented the mathematical explanation of it. Nowadays, we have computers that they have the number inside. We don't know what they do, but produce a result which, technically speaking, should be an explicit demonstration of the construction, but it's not. It's completely implicit, and therefore there is not understanding of the making of the building. For instance, I was thinking before when he was showing the snail, this snake, and the spider. Louis Kahn's section of the Kimball Museum, the vault, is parametric. There's no question. It was never mentioned during the time of Louis Kahn, not even now, because nobody is going to read how that was generated. And I think what is very important, I thought there is no presentation of architectural building, is to understand how implicit as became the acceptance of parametric system without understanding what it is and what it does architecturally speaking. And I think that is the great contribution of this lecture.
Bernard, would you like to respond to that? Or that's not a question. Marco, would you like to pose a question?
No, okay. That's a very kind statement.
I think that I found it very informative. I want to say thank you to start off. I also just in bringing it back to bringing the mathematics back to the geometry. What I thought was really fascinating is that the computation was kind of developed with the mechanism. I would expect that there was some understanding, and again, I think that moving to the War machine was quite fascinating because that's something that in the end of the day, it really just needs to work, and those things have to be applied in a particular way. I think that the problem with the parametric design that's commonly discussed and explored, I would say, especially within a setting such as the university, is that there is only kind of one step to it. You're operating with, you're producing, as you've shown, from mathematics and from geometry, but without taking it out of the system and actually getting the War machine on the field per se. You're not actually producing anything of any particular meaning. There's no way to test what this thing is and if it is meaningful. Could you talk a little bit about how you think that architects and students and professionals can start to move this kind of way of thinking, I guess, have a dialogue between the kind of mechanism and the mathematics at the same time, without leaving it in the system as a kind of geometrical form, but also bring it out and apply it. And if there's any kind of way to create a relationship between those two processes. Do you understand the question?
I understand, but it's a very vast question, and I think there are many different ways to use mathematics with computers nowadays. So there are people who like to program, there are people who are using parametric software, which in a way are in themselves a program. So they are programming. And I think it all depends of the various personality of the people. I think there is not one single way of using mathematics for designing.
Could I ask how you use it for designing?
Well, I'm totally embedded into the software I demonstrated, which is a new platform from Missler, which is Top Solid 7. So it's a kind of, well, in France, a big company that have a lot of money, and especially state money, use CACHE. But company who need to control their budget are using Missler, especially into the production field. So what I showed you today is just the design part of the software, whereas it is mainly due to generate ISO code for numerical command machine or this type of things.
Could I ask another question, I guess, kind of maybe to follow that up, more specific? Do you think that a building form, and again, if we talk about that, do you think a building form generated in this fashion has any more kind of implicit value or implicit human connection than a building form not generated from, you talked about these are things that you cannot generate with a pencil and a ruler. Do you think that the buildings have a different kind of value, or are they simply just different in form using these things? And again, I would go back to the War machine. That's something that just has to work. But when you're just dealing with static form, a generated static form, does the form of it whether it's generated from this kind of geometrical thing using something like the software you're using, do you think that the architecture coming out of it is, what do you think that the benefits are? Do you think it's better? How do you think it, and how do you think it would be?
Well, the first, there are several steps into my thinking, and tonight I just presented one. First of all, I wanted to demonstrate that what we see nowadays is not at all foreign to the classical tradition. And actually it is because, you have, for instance, edition of Vitruvius, where people just limit themselves to present the 7 first book. So, of course, if the book on mnemonics and the book on mechanics is not even provided to the reader, they don't know about it. This happened several times, even in modern times. The first thing is that I want to explain to the people, to persuade them, then if they read the classics, they are not studying something that is totally foreign to what is happening, and that the most crazy shapes that you see nowadays could be designed with classical methods. Then there is the question of should we use parametrical model in order to produce varying spirals, columns. I think they must remain an exception, and I think the parametric conception is not a question of style, but a question of method. And that then even knowing parametric design, people were still building Greek temples, I would say. And I think that nowadays, especially with the crisis, parametric design should be used in order to provide more adequate building at a lower cost. And I think that the issue about curvy surfaces is not relevant for the current period.
Good. I don't know if in the end I'm going to have another question, but something I want to point out is when I was a student, my professor of drawing was always upset if we used templates to draw a circle. He kept telling us, you have to use a compass. It was forbidding completely all the use of templates. We had to use compass, we had to use strings, stuff like that, like it was demonstrated. And I think that is what is happening now, is people that are using parametric design are using templates, are not using compass. And let me tell you what is the big difference, is especially in the 10th book of Vitruvius, talks about a war episode, and use a very special word that I'm sure you will agree. The word he used is solertia. Solertia means something that is cunning intelligence. And tell a story. There is a city who has an architect who does his war machine, and they think that it's doing too much traditional war machine. They want this guy, like Peter Eisman, guy, who is going to do this fantastic machine with fantastic shapes and so on. They feel him going war, and the machine don't move. They are too big, too strange, too unusual. So they go back to the other one and ask, please help us, we're going to lose. And this guy said, take all the water that you have in the city, the manure, the sewer, and put all the stuff around the city so the machine of the other guys will get stuck. That is solertia. And that is the problem, is if you are using the compass as a tool, you have solertia. If you are using the template, you don't. And I think that is the problem of not understanding what is the dimension of classical design. There is a lot of cunning intelligence. They are really working, and it's another sentence of Carlos Capra says, when you design, you have to be like a thief, trying to figure out what's going wrong. And right now, When you use a parametric and you make all this curve, there is no understanding of what can go wrong, because the machine is perfect, but the reality is not. So there is a difference between the template and the compass.
Well, I'm glad you mentioned this, what is actually the conclusion of the architecture, because one of my texts in my latest book, Projectile, is dedicated to precisely the fact that architecture, the architecture ends up into human shit. La merde en français, quoi. And I think it is a kind of critical and very pessimistic position about the abuse of technology. That's for sure, and it's something we should listen to very carefully nowadays. But still, technology is there. Vitruvius was a military engineer. He knew of the cube duplication involved into dimensioning the diameter of the spring. So, of course, you have to learn several things and put them together.
I was just wondering, in relation to the compass and where does the software like this sit for you in that? Is it a compass or is it just a model? How do you, in terms of once you abstract it into a tool, the tools of software and the variety that there are, where do you see it being in that?
It depends from software to software. There is software that are compasses, and there is software that are templates. And I think that is that you have to develop a critical mind to decide which one is the one to use.
I guess I was meaning in relation to something more complex like this that we're looking at tonight. It seems that it's more of a compass, but I don't know much about it and how it works. How is it for you?
Well, for me, there are software that are drugs. So they are nice to consume at the moment, but in the long run they are very harmful. So, for instance, SketchUp or this type of software, I think you must use tools that really train your mind, and in the same time enables you to really go to fabrications. So I would have a tendency to distinguish between drugs and other products.
So maybe this is more like alcohol?
Perhaps.
I just on that point, I do agree, and I just wanted to say something else. When I was a student, not quite as much more recently, I was told that if I used a computer in my first year that I would be failed, and I was to do everything with pencil and ruler. And so maybe we're coming around again on the wheel. But I would just kind of ask again. I think maybe more, and I don't know how to phrase it perhaps differently than I did, but you have the software here, and we see it. And I can't help but think, watching Dürer's the spider, the second one you showed, that itself is a kind of drug of nostalgia, in a sense that the geometry, when you did it, people said, "Oh, that's really interesting." It did the double curve, and then you modified the parameter, and it did it again. In terms of, and you just mentioned like applying it towards building better buildings for economic and other things as well. Do you think that again this kind of framing the conversation through a background as classics and Vitruvius, do you think that itself is a kind of distraction away from the true potential of this as a means of generating architecture? I mean, I suppose I personally am afraid that we'll find another toy very, very soon, and we'll get kind of stuck in it the way we got stuck in AutoCAD a couple of decades ago, and the way that I think people are getting stuck in other things. it very quickly becomes attractive for some reason that we don't quite understand. The way SketchUp, you can just pull the pieces, and how attractive is that? But it's so far removed from reality. In my mind, still seeing the software, there is an immediate attraction to it, but there is also this removal from knowing how to apply it. How do we avoid that? How do we not get stuck in that trap yet again?
I'm working with a software company, and I can swear you, when I was young, there was no computer. So I don't think. I think you must train yourself in a way that you are not, adapted to the software of today, but that you are adapted to any type of software that could come up within the next 50 years. And most probably, this means more studying mathematics and all of these things, rather than just be very quick on any type of software. And you must understand the logic behind the software, rather than the software itself.
But isn't there sort of there's a tension in there with understanding the logic behind the software, but the software is a tool, and that the best way to hone and get something out of it that is beyond what its normal capacity is to be good with the tool. So I can understand the fundamental logic behind the software, but that doesn't mean I'll be able to get something interesting out of it as a user, as a tool.
No, of course. Software is just part of the education, and you can also read the classics.
In that line there is a term that is used in many offices. They talk about CAD monkeys.
Yes.
And I think there is also the risk of having parametric monkeys, in the sense that is the use of this software. They use CAD without knowing what CAD is about. And the same is the other one, is they use software without knowing what software is. And the use, for instance, of SketchUp, which is a template, is a tragic thing. It's not something that is really giving you value of understanding. But of course, it's much easier. It's like using a template and doing the circle is much easier than using the compass, that you have to find the center, you have to draw this and do that. You have to know what the compass is doing. That is one of the big problems that we have architecturally now, which is the lack of education of the architect in expliciting what are the phenomena that he's dealing with.
And I guess the question then to you, Marco, would be how do you reintegrate that? And I think that, again, one of the things that these tools are doing, and maybe a drug is again a good metaphor, is because it's giving you instant gratification, which is what a drug does, rather than working for it. So how do we embracing the tool go forward with that kind of warning in mind? Do you give a thought on that?
You have to use to learn the tool for playing. We use compass like things to throw against the wall and to make center. It means there is a different way of looking to that. I cannot do anything with the template, but with the compass, we could play, make circle on the wall, and then hit the center. So that means you have to take SketchUp and go against the rule of SketchUp and see what are the forms that are coming up. Then you learn. But if you just follow the tradition of SketchUp, there is no way you can learn.
Can I interrupt that? Bernard, could I ask you to address, do you think actually, given the aspect of what you've spoken about the digital, do you think we are preparing students adequately enough to work in this area?
Do you
think that we are preparing students adequately enough in the area that you are talking about?
Well, I do not know your institution.
I don't mean our school, I mean in general, what we were talking about.
I think that clearly the link between software education and culture is really missing. Yes, this I think, that personally, because I'm working into this field of CAD/CAM, I see now nearly no difference between reading text in Greek mathematics, and then there is a continuous transition to mathematics, to mechanics, and then mechanics to architecture. I do not have a general solution for architecture. It is not my point. But I think that on the basis of this continuity, we can look at architecture on a different angle. And it is really essential to bring back the bridge between culture and those tools that were actually cultural tools.
Can I ask you about the fabrications? You wrote that first book for MIT Press in 1995. I assume that you set up the Object Teal factory. Could you say a little bit about how your factory works as a factory? You've obviously not gone into architecture in a certain way, you've gone into it in another way. What sort of, I noticed the phrase furnishing the territory. Could you explain a little bit and why that, in a way, as you hinted last night, may be coming to an end? What's going on at the moment?
Yes, well, rather than furniture, it's more, I would say, architectural components. Well, for several reasons. It is because that to keep up with what is happening into software and these type of things, you must already dedicate nearly the 24 hours of the day. So you cannot have the life of an architect that is that has to visit customers and do many, many other things. So I have more interest into having the tool evaluate and collaborate with this software company. So I prefer to focus on two problems that other architects have difficulty with. So we do special parts into building rather than building themselves. And we are glad with it. So it's a question of personal interest. I think that unfortunately people think that there is only one kind of synthesis that the architect can do, which is you start by the program, then you make the project, and then you have the construction site and so on. I think that to deal with components that are used throughout several types of buildings and capitalizing the experience in order to have these components evaluate. This is pretty much the way Japanese architecture office works. That means they have an architectural office would be distinguished by his type of windows, his type of doors, and so on. And because they do it in a special way, and especially they do that on the long run. And I think that this is also one thing that is missing in architecture, is the possibility to work on the long run, that rather than just on a project basis, for one single occasions, rather than reinvent the school one day, then reinvent the house. The capacity of focusing on a certain type of problem, like housing, and improving it rather than reinventing it is very important. In the industry, you never invent from scratch. There is no engineer that starts with an automobile and say, how many wheels will we make on this automobile?
Okay, if there are no more questions or anyone from the audience, I have one closing question. Why do you think Europe was not able to profit from a freeware like Linux, and we are a slave to Microsoft?
Yes, well, this is, I don't know, I think the passivity with which we receive the software and especially the lack of initiative of the European community in this field, because, well, I'm using a French software, and in terms of CAD/CAM, CATIA is French. We still have a lot of very good software industry in Europe, and Linux is a real open and free system, and unfortunately, I think in Europe there is only the case of München in Germany, where the municipality decided to switch totally from Microsoft software to Linux-based software and make it a public tool. The passivity of Europe is desperating.
Last question, okay.
I would just say quickly on that note, Android is coming.
All right, the Android is coming. bernardCACHE, thank you very much for coming tonight.
Thank you very much.
Thank you, man.